Hello, can you hear me?
Yes, we can hear you, Badri.
Okay, good. So I will talk about understanding powers of black holes and neutron stars from GW observations. And I want to first of all apologize for not being there, and I want to thank the organizer for accommodating this talk remotely. So the talk will be in two parts. The first is I'll talk about the Inspiral-Merger ring-down test for binary black hole mergers, and the second one actually belongs in the next session on neutron stars. So I'll be talking about constraining neutron star equations of state and radii from the BNS event. And I also want to make the point here that if you do have a model for NS EOS which is not which is in alternate theories of GR, then I think this is how you would actually do it. Okay, so let's start. So I want to start off first of all with the Inspiral-Merger consistency test. And as you know, so the standard model of GR, so if we have two curved black holes, let's say masses M1 and M2 and spins chi1 and chi2, so when they merge, they form another black hole, which is a mass MF and chi-F. And in standard GR from numerical simulations, we have a reasonably good idea for how, given an initial two black holes, how what the final parameters are. And then the question is, can these effects be checked observationally? And in a similar vein, it's not just the mass and the spins, but there's also other constraints on these parameters. For example, the area increase law will tell us that the areas of the two black holes, A1 plus A2, have to be lesser than the final area. So you could also test a violation of this inequality, and this would be a test of, for example, violations of energy conditions near the horizon. Then if you, so now I want to go on to the first BBH detection, 5914. And if you just recall here, the initial masses for this event, the M1 and M2, are 36 and 29 solar masses. The initial spins are consistent with 0, more or less. And based on these numerical fits I mentioned, you can compute that the final mass and the final spin have to be 61.8 and 0.67. And again, here you should keep in mind that this value of MF and chi-F are obtained from numerical fits, so this is not an independent test. And similarly, if you were to compute the areas for the final black hole with these parameters and compare the initial area, so these again all be consistent with GR, so this would not be an independent test. So what you want to do is you want to measure the final parameters and the initial parameters independently of each other. And this was the motivation between the LDC publication in 2016 and also the methods paper by Ghosh et al. In 2016-2018. And they have the following procedure. So you choose an intermittent frequency. In this case, it was around 130 hertz. Let's call the frequency FC. But really what you do is you take the Fourier transform H tilde of F and you break this into two components, a portion below this frequency and a portion above this frequency. And for each of these portions, you estimate the parameters of the waveform, which are the masses and the spins. And again, keep in mind that the portions of the wave, or these two portions, depend on the same parameters, M1, M2, chi1, and chi2. And then you convert these to distributions in the parameter of the final black hole, MFAF, using the fits from numerical simulations. And then it's straightforward. Then you compare the two distributions from these portions, and you see whether they overlap or not. And this is one of the results from the first detection. So here what you see in red are the contours in MF and chi-F, and the ones in yellow are the ones from the post-inspiral, the portion above FC. And you see that these two overlap, and they also overlap with the black region, which is what you get from the full waveform. So this is a nice consistency check, and it is an important result that this actually worked in that case. But keep in mind that the waveform portions split in frequency are not the same as splitting them in time. And the two things can differ, especially near the merger, where the waveform frequency is evolving quite rapidly. A different approach is to do something, is to say that, well, I don't want to cut in frequency, I want to cut in time. I want to fix a time, let's say some cycles after the merger and some cycle before the merger. And then I want to measure from these two portions the parameters independently. And then I want to do all these tests that I said. So which is, again, check whether these fits of the numerical, from numerical simulations are accurate or not. And also check things like the area increase law. And so I just want to here illustrate this with an example in which you're testing the area increase law. So these plots, let's look at the first one or the second one for the moment. So this is a simulated signal. And what you do in this is you take the blue portion, which is the part of the waveform at an early enough time before the merger. In this case, you're cutting this entirely in time. And then the orange part is a part of the waveform which is after the merger, that is a ring down part. And then the goal is you want to take the blue one, estimate the parameters before the merger. You take the orange one, estimate the parameters after the merger, and then you compare, and then you can test the area increase law and also, in fact, all the numerical relative fits as well. And the next slide shows an example of one of these results. So don't focus on numbers, just focus on the plot for the moment. So the line in yellow is, so the plot shows the distribution of the ratio of the final area to the initial area. And the shaded region on the left, so that is the one which starts at 1 on the x-axis. So anything to the left of the white region, so that is a violation of the area increase law. Anything to the right is the law being satisfied. And the yellow line shows, based on the priors we had in the study, on the masses and the spins and so on, what the priors on the ratio of the areas are. And the other distributions are two cases. The first is for comparable to O1 sensitivity, and the dashed blue line is the one corresponding to LIGO design sensitivity. Then you see that the best you can expect for an event like 5914, what we can do with O1 data, is not so different. I guess a bit different for O2 now. But really the main change will be when we reach design sensitivity. So what you see is that for an event like 5914, you could sort of confirm the area increase law with a probability of 75%, but this really increases to more than 99% for when you reach design sensitivity. And in this context, I also want to mention an important technical work. This is due to Colin Capano recently, and this is in preparation. So the important point here is that when you cut the waveform in time, you have to be very careful. So this plot here shows an example of what happens when things go wrong. So in this case, what has been done is that you have a full waveform and you made a cut at a particular time. And then you want to measure the final mass on the final spin, and you see that the red lines, which are the actual injected values, those are outside all the credible intervals. And this is happening here because you were not careful in doing this cut in time. So instead, what you want to do is you want to say that in this plot you have, in this next slide you have, let's say data samples xi, and you want to exclude, let's say, indices I between, let's say, uppercase I and uppercase j. And in this case, what you have to do is that you want to sort of take the covariance matrix of the data, which is a Cij inverse, which is something that you compute from the data. And in fact, the Fourier transform of Cij is precisely the power spectral density. So what you have to do is you have to exclude the entries in the Cij with in the right ranges, and then you do the inversion. Otherwise, the whitening procedure can lead to wrong results, like in the previous plot. But if you take this into account, then what you get is something that is completely consistent with the actual result. That is the next slide. Okay, so let's now change topics and let's go to the neutron star equation of state measurement. And again, as I said, this really belongs in the next session on the properties of matter at extreme conditions. But again, if you had an alternate model of GR and you have some equation of state that you want to test, then the procedure I'll describe now is the way you would do it. And this is a result of a forthcoming work that should appear in the next week or so, I would guess. So the essential ingredient here is that we want to constrain the equation of state of the neutron stars in 1708-17. And we assume here that the neutron stars have identical equations of state, and also we take all the information from electromagnetic observation for the sky location. And we assume that the neutron stars have what are called tidal polarizabilities, lambda 1 and lambda 2. So these parameters tell you how a neutron star responds to an external field. And the problem then becomes that what do you do with lambda 1 and lambda 2? So you have some equation of state, and based on that you can compute lambda 1, lambda 2. But you're sampling in these procedure for estimating the parameter, you're sampling the masses and the spins. So you have to then do something for lambda 1, lambda 2. And so I claim that the right approach to do this is to actually sample not in lambda 1, lambda 2, but the sample in the space of the equations of states directly. And from that you compute lambda 1, lambda 2 as a part of the parameter estimation procedure. So in the next slide, this is a theory that we are actually testing in this study. So we look at an effective field theory for QCD. So this is what is called as chiral effective field theory. And this is meant to capture the effects of QCD at the energies relevant for, let's say, nuclear physics and for a neutron star. And this theory considers essentially, models the nucleus as essentially pure neutron matter, and is expected to be valid up to roughly twice of nuclear saturation density, where this NSAT is roughly 2.7 times 10 to the 14 gram per centimeter cube. And this theory systematically includes all the effects of two-body and many-body interactions, and also as a byproduct based on these quantum Monte Carlo studies, they also produce errors, systematic error estimates of all the parameters of the EFT. And we consider then two models. The first is this chiral EFT valid up to twice of the nuclear saturation density, and the second one where we take it to be valid only up to NSAT. In either case, you extend the EOS to higher densities, respecting causality, stability, and also you say that the EOS has to allow masses corresponding to the heaviest observed neutron star mass. And then what you do is you generate a couple thousand equations of state randomly based on the parameters of the EFT. And for each of these 2000 EOSs, you solve the TOV equations, and you get the mass-radius relation and the tidal polarizability. And then you're in business. Then when you sample now in the masses, you can then also sample randomly from these EOSs that we've selected. And then for each of these cases, then you have the values for lambda 1, lambda 2 completely consistently without making any additional assumptions on how these should depend with any approximations. So here you do ensure that the two stars have the same EOS and the lambdas are entirely consistent. And we sample in the space of EOS with a prior which eventually leads to a roughly uniform prior on the radius of the neutron star. And there's one more constraint that we put in. We assume that just after the merger, what you get is not prompt collapse, so you get a hypermassive neutron star at least for a short time. And the next plot then shows an example of the results. So this is in the mass radius plane. Let me describe the different aspects that appear in this plot. So first of all, each of these curves in the mass radius plane, this is all the 2000 equations of state. And in this case, this is the chiral EFT up to nuclear saturation density. The contours in blue are the contours for M1, and the ones in orange are for M2. And the red dashed lines, so between 1 and 2 solar massive, these are the priors we have in the parameter estimation. And then the dashed red line is the upper limit that we put on the threshold mass for not having prompt collapse. That's probably through 2.35 solar masses. There's further details here which I don't have time to go into. And each EOS is the shade of each EOS tells you the posterior marginalized probability for that EOS. So that is telling you how likely that EOS is based on this study. And you can see the distribution for radius and the masses in the 1D distributions. And you see, first of all, from this that you already exclude all the values of so all the large radii so above, let's say, 12 solar masses, 12 kilometers. So I'll describe this later in the next slides. If you repeat the same procedure for, let's say, the same Chiral EFT up to twice of nucleus action intensity, so this is a more constrained model, so you don't have to extrapolate the equation of state for all that much. So in this case, what you end up is a tighter, well, the constraints are roughly the same on the radius, but the EOSs that you are considering are much narrower. So in this case, you again see the limits on the radius are roughly the same. It's about 11 kilometers. And then in the next slide, let me just show then the results with all the constraints then put in. The first plot shows, the first panel on the left, this shows the priors that we have effectively for the radius of 1.4 solar mass neutron star. And so the one in blue is the prior that effectively that we have for the, okay, just the last slide, so I'll just finish now. So this is the effective prior that we have for the radius. And the second one is a result of the GW parameter estimation. This is the posterior for the radius. And then the next one, which is the one I want to highlight, the third panel, this is the tightest constraint on the radius that we have so far. And this is based on the constraint, again, from the GW and from this constraint that the total mass of the remnant must be lesser than the threshold for forming a hypermassive neutron star. So I'll stop here, and the rest we can have in questions. Thank you.
Questions?
Badri, thank you very much. Very clear talk. I was wondering, in the first part of the talk, you're essentially sacrificing some signal-to-noise ratio in between where you say, okay, an earlier part and a later part. Right? Is it not possible to state the theorem in such a manner that you can use the full waveform? Why sacrifice some signal-to-noise ratio?
Yes, indeed. So you do sacrifice some signal-to-noise ratio. You're completely right. So, and indeed, you could have a waveform model which includes some of these effects in it, and do a study with that. So here, the idea was that you do sacrifice some SNR, but you have weaker assumptions. So the assumption, so the philosophy here is that the weaker the assumptions are, the stronger the test is. So in other words, if the test were to pass this, the procedure I said, which does have a smaller SMR, but it's a stronger claim because you're making fewer assumptions at the end of the day. So you could do both, and this would be the more stringent test that the data has to pass. And if it passes this test, then you have made fewer assumptions, therefore you believe the result more based on this.
Hi, Badri, this is Sukant. I have a question on the second part of your talk. So when you build your TOVs...
Sukant, sorry, I can't hear you.
Can you hear me now?
Yes.
Okay, so when you build your TOV stars, so you say you use the Chiral effective field theory up to a certain density. You have two different models for that. But what do you assume for the outer crust as well as the equation of state for the core?
Yeah, so the equation of state is valid also for the crust. It also includes effects for the crust. And for the core, so you can also have phase transitions in this EFT. So in fact, in several of the plots I showed, if you look carefully at the equation of state, you will see a phase transition there. So this includes all of those effects, the way that the sample of the EFT has been chosen here.
And how do you ensure that your stars are thermodynamically stable?
Okay, this goes into some more detail. So this is essentially, so this is based on more of the details of the construction of the EOS, and this would take too long to explain at the moment. So essentially, the speed of sound is, for example, you say that for a given EOS, you come with the speed of sound, and we require that this is less than 1. And there's a long procedure for extrapolating the EOSs to higher density, which unfortunately I don't have time to go into it. This would take just too long at this point. But this is all based on these quantum Monte Carlo calculations, which do this, compute the Lagrangian, and then they have all the constraints on the parameters of the EFT.
Thanks, Badri.
Let's move on to the next speaker, and we will have time to discuss at the end of after all the talks are finished.